but very often this is being misclaimed. Now, once again, from a conceptual point of view, these relationships are really cool because each and every term here is exactly measurable, in principle measurable from the experiments. In particular, this term is nothing else but the linear combination of higher order moments of the position. Now, so notice here that here I have not said what kind of X and P are. I just said that this is some dynamics and recorded expectation values of X and P over time. So if you're to solve, if you're treating quantum case, then we are going to represent expectation value by means of Dirac bracket sandwich, and more importantly, we are going to say that the observables are given by self-adjoint operators, and X and P obey the canonical commutation relationship. This is really, really important bit. And then finally, if the state evolves unitary, then Stone's theorem tells us that there exists a unique self-adjoint operator H such that this constraint or relationship takes place. However, it does not specify what H stands for, besides the fact that it's just self-adjoint. Now, so what we have right now on this slide is a system of like a very heterogeneous system of equations. So some equations are relationship between functions of time. Some relationships are between functions of time and these sandwiches, and some are actually matrix relationship, operatorial identities like commutation relationship. However, it turns out that that you can treat these equations as system of equation with respect to H as unknown. And what's interesting, you can solve for this H. And by solving this H, you actually obtain unique operator of generator of motion, Hamiltonian quantum Hamiltonian. So this is how we could rederive the Schrödinger equation by starting from the Ehrenfest theorems and adding to them the Heisenberg computation relationships, and we arrive at the Schrödinger equation. So in this way, the Ehrenfest theorems are more fundamental than the Schrödinger equation. The Schrödinger equation could be Ehrenfest theorems could be made into axiom, upgraded into axioms, and the Schrödinger equation can be made as a consequence of the axioms, unlike sort of it's traditionally done, where it's the opposite stance. So let us take a look and see what's going to happen with this technique if we actually try to change conditions. So let us still keep the Ehrenfest theorems as it is, as given here on the left, unchanged from the quantum case. And let's keep the right-hand side still the same, except let's make the X and P commute, right? So this is the only difference we're going to change. We're going to change the X and P commutation relationship between them. So obviously, this can no longer be quantum mechanics because X and P does not obey canonical computation relationship. So if we apply the same techniques with respect to unknown generator of motion L, right? It turns out that in order to obtain like a self-consistent, really meaningful solution, we need to introduce an additional, as we mentioned, hidden variables, lambda x, lambda p, such that they're conjugated to X and P correspondingly. And in that case, the dynamical equation takes this form. And I would like to emphasize here, it's a very interesting part, is that that there is an ambiguity that any function, any real function of X and P could be added, and it does not change, underlying dynamics, observed dynamics, so-called observed dynamics. So, so this is actually we obtain, in fact, a classical mechanics in Hilbert space. So now it's up to us to choose to utilize this freedom. And I have to say that this freedom, the meaning of this freedom was not fully realized, recognized until Cesare pointed the importance of this freedom. And so there are two important cases. The first case is as the straightforward one is when we set this function to 0, and then we obtain the well-known, the Koopman-von Neumann equation of motion, written in this operatorial form. Now, but there's something more interesting, because nobody says that we have to keep X and P, this term to be 0. And in fact, we can change it to be of this form. And in this case, we recover what Cesare called the Koopman-van Hove classical mechanics. This is a very important classical mechanism. Cesare will talk in his part of the talk more about it. It's interesting thing is that this term, additional term, is actually Lagrangian. Is Lagrangian, and due to the dimensionality reason, it has to be divided by h bar. So it's a very interesting thing is that the h bar appears in purely classical physics here. And just I will briefly mention the Koopman-van Hove has very important covariance properties, gauge symmetry properties on the phase space that will be explained later. So I would like to here give a bit of, once again, intuition behind the classical Liouville mechanics and Koopman-von Neumann classical mechanics, and as well as Koopman-van Hove, is that in a Liouville mechanics, in all the mechanics, we have characteristics in the phase space. Like the underlying trajectories in phase space are identical for all classical mechanics. However, the way the weight attached to trajectories differs significantly. For example, here you have in Liouville case you have a strictly positive probability weights, because these weights have interpretation of probability, and they remain constant along the characteristics. In Koopman-von Neumann's case, actually the shapes of the characteristics are the same as I said before, but the weights can be different. They can be complex, they can be negative, whatever, as long as the expectation value square of the underlying weights, which are given by the Koopman-von Neumann wave function, are exactly match the characteristic, the probability weights of the classical Liouville mechanics. So there is a fundamental thing about Koopman classical mechanics in Hilbert space is the existence of the Koopman-von Neumann mechanics is the existence of the Born's rule. And Professor Brummer will talk about this on Wednesday. So I'm looking forward to the discussion. And again, this Born rule emerges in Koopman-von Neumann mechanics simply because of the fact that X and P commutes, and therefore the complete basis has to have both X and P labels to be used. And this is due to this Born rule, the observation, the Koopman-von Neumann reproduces exactly the same as classical mechanics, as a classical Liouville mechanics. Koopman-von Hove goes one step further. Koopman-von Hove actually allows you to change the weighting along the trajectory, but again, it will still obey the same probability distributions. It's interesting enough to I wanted to use this to advertise Richard McCall's talk on Wednesday about path integrals in Koopman-von Neumann mechanics. So path integration formulas is also exist in this classical physics in Hilbert space. So let us talk about phase space representation. And the phase space representations actually are formulated within this framework in the following fashion. So let me just recall that the quantum case and classical case were only differed by the commutator. The only difference, everything was kept the same except the commutator got changed. So this is restated here, right? So we had a different algebras in the classical case of observables and algebra in quantum case. So let us. The only actual difference, fundamental difference, is that the number of sort of generator of algebra is different in classical mechanics, whereas quantum mechanics. Quantum mechanics is just two sufficient, but in classical physics has to be extended with these two hidden, hidden variables and lambdas. And so, for that reason, to make it on the same footing, let us actually introduce a kind of extended quantum algebra, where we'll introduce also hidden variables, which we denote here by theta, just to be symmetric, just to be one-to-one with classical mechanics. But more interesting is that let us modify the computational relationship between X and Q, X and P. And you please note that I use right now a different label for them to signify the fact that these are different operators than in these cases. And what we are gonna slightly amend the computational relationship by adding a dimensionless parameter kappa, IH by CUC becomes IH bar kappa. So when kappa is 0, the algebra commutes, and in fact, this extended quantum algebra exactly looks like a classical algebra. And when kappa is 1, this looks sort of like a quantum case. So kappa parameter here, dimensionless parameter kappa, is degree of non-commutativity. So if it's 0, it's purely classical physics. It's 1, it says quantum physics, and it could take intermediate value. Now it turns out that these actually, that the classical and this extended quantum algebra are in fact isomorphic. You actually don't need to even sort of use the same different notations in principle. And a very important example of isomorphism is which looks like exactly like Bob operators in the Wigner function theory, is given by this connection between this relationship between the position, the quantum position and the classical position, and the conjugate, this hidden variable, which are actually Bob operators again to make this connection with the Wigner function. And as you can see here, that the thetas and lambdas are the same in this case, in this form of isomorphism. And PQ is given by the classical P plus this lambda x hidden variable Bob operator in classical physics. So this is an example of isomorphism. As the isomorphism are present, are possible, but this one is particularly useful for the reasons as I will explain in a second. So let us go back to this framework, and let's change the input. Let's just simply relabel the Ehrenfest theorems. Right now we're going to say that they're the same. They're observationally they're the same, but the only thing that changed here is that we use the label XQ PQ, this extended algebra, right? Extended algebra, which unifies both quantum and classical case. And now we are imposing that, as I just said, that we need to solve with respect to the extended algebra, and we are not specifying the value of kappa. Kappa is allowed to be free parameter in this formulation. Surprisingly, this is very important addition, and it's going to change. It's going to change how the generator of motion looks like. And as you can see, the solution is given here, and it has this interesting bit. This looks like a Schrodinger case, exactly like a Schrodinger case, one-to-one, plus this free function, very similar to the classical case, right? To the classical case free function that we explored earlier. And the important bit of it is that it actually has a specific structure. There's a specific structure of arguments. And kappa sort of enters, kappa here enters multiplicative to h bar. You may notice that 1 over kappa is over here, but nevertheless there is h bar over here. So if you multiply by kappa, kappa will be multiplicative factor of h bar. So again, let's just try to explore the choice of the free function. So if you choose the free function, this free function to be of this form, basically minus Hamiltonian, then we arrive, this unified generator of motion turns into the equation of motion for the Wigner function written in the Hilbert space. Accidentally, this is actually this formulation of the Wigner function leads to a very efficient way of solving a Wigner equation of motion. Moreover, the classical limit of this generator of motion coincides exactly with the Koopman-von Neumann mechanics. So and this is really important. This is starting point of a longer discussion given here by us that actually Wigner function is itself the Koopman-von Neumann wave function. So there's no kind of mystery in this case why the Wigner function is negative, because it's Koopman-von Neumann can be negative, so no problem there. So this is an overlook connection between Koopman-von Neumann and the Wigner functions, and it sheds light on these discussions about meaning of so-called quasi-probability. There's no need for quasi-probability. Here's an example of the evolution of the initial state in the phase space, which is being here about by Koopman-von Neumann and the Wigner. So you can see. You can see that the evolutions are different, even though the states are sort of maybe initial states are the same. Now we can do more. We can actually change the free function to take a different form, a very different form, like this. Means minus Hamiltonian and minus Lagrangian, or rather take Koopman, the previous choice, minus Lagrangian. In that case, we obtain, to best of my knowledge, a new formulation of quantum mechanics in phase space, which we decide to call quantum Koopman-van Hove formulation, because its classical limit, the kappa goes to zero, the commutative limit of it is the classical Koopman-van Hove mechanics, as presented earlier. And we believe that this is actually this formulation, this new phase space representation of quantum dynamics will let us soon derive the hybrid model that Cesare will present as a classical limit of this new quantum-van Hove phase space representation. And this is sort of in a way a reply to Professor Capral's talk of yesterday, by showing that our model perhaps can also be derived as classical limit, but of different phase space representation, not the Wigner phase space, but this new, to the best of my knowledge, new phase space representation of quantum mechanics. And here's actually some illustrations actually of this Koopman-van Hove for a harmonic oscillator initially in the Gaussian state. So if it were a Wigner evolution, the initial Gaussian state would actually will be constant, will be Gaussian red, and there will be no imaginary part will be zero. But this is Koopman-van Hove. It has both a real part as well as the imaginary part, and you can see that actually in the quantum case kappa equals to 1, it undergoes kind of significant interesting dynamics. And for example, if you take some quasi semi-classical part of a kappa is not 1 and not 0 in between, it actually starts looking more and more like a classical evolution, means it becomes more and more stationary. But again, please note the emergence of the imaginary part, because Koopman-van Hove has this imaginary phase. And finally, I wanted just to mention that there was an earlier work on using ODM in 2014 to put some interesting observation about hybrid quantum systems. So in this work, Radonjic and co-authors started from two Ehrenfest theorems for two different initially quantum particles, and such that there was this the interaction between two quantum particles has to happen through this W, this potential interaction term. It turns out that if you want to have a hybrid and obey this Ehrenfest theorem shown here, it turns out that this coupling potential also they showed must be a function of one of these hidden Bob variables. And this is very interesting, and this actually turns out to be they claim it to be generalization of the. This shows that this is sort of generalization results presented by Professor Turner in earlier works. And then finally, I'll just outline before Cesare starts is that we have this Andre, the chair of the session, who had a talk on Wednesday about application of this framework to the Dirac equation, and there are very interesting results with the spin. What happens to the spin classical limits? There was some work by Ždano and Seidemann about topological non-trivial spaces, and also we have ourselves did quite a bit of work on open quantum system dynamics, and very interesting recent preprint that we have online about entropic gravity in some experimental tests suggested by this framework. So Cesare, I hope I didn't eat up all of your time. I'm going to stop sharing.
Okay, so that's here to Cesare now. And you should ask questions later.
Yeah, I think Cesare is muted.
Cesare?
Right. I am unmuted now. Right, okay, so let's see. So this is a story of how we tried to rescue a model that was proposed long ago by George Sudarshan in '76, and over the decades received quite a lot of criticism. And when Dennis and I met the first time, we were discussing this kind of models, and we eventually realized together with François Gay-Balmat that we could actually do something to fix those. So let's see, or at least partially, let's see how it works. So I will restrict to talking about quantum classical models based on wave functions, as opposed to quantum classical models based on phase space densities or density matrices. So I don't know why, okay. Yeah, so yeah, I'm aware of two classes of models. One was by Sudarshan in '76, that was based on Koopman-von Neumann that Dennis just introduced. And the other one that has not been referred to so far in this meeting is due to Hall and Reginato, who proposed an alternative going back in spirit, at least, to Nathan Rosen's classical equation from '64. And I invite everybody to pay attention to Reginato's talk on Friday, but also to look at Schleich's paper from 2015. So both models are Hamiltonian, which is the key word in this talk, and as they can be obtained from Hamilton's variational principle, but they carry their own difficulties. And as I said here, we will rescue, or try to, Sudarshan's model by modifying the underlying KVN construction. So this is a quick summary of what Dennis just said. So this is the Koopman-von Neumann equation. This is the self-adjoint Liouvillean operator. And just to give you more details, Sudarshan took the tensor product of this kind of phase space wave functions with quantum wave functions and studied their evolution. Eventually, he invoked super selection rules, and at the end, this led to interpretative issues that were discussed later on, mostly by Perez and Daniel Terno. So let's look, since we are talking about Hamiltonian systems, let's look at the Hamiltonian structure of the Koopman-von Neumann equation. So this is the Dirac-Frenkel Lagrangian, which is well known to most quantum chemists. And let's make some comments just by looking at these Dirac-Frenkel Lagrangian. So first of all, we notice that the total energy here involves a different distribution than the one that's prescribed by the KVN theory. And unless one enforces singular phase factors, this may be an element of ambiguity. And I refer to Elon Joseph's walk from last year. Another minor point, if you like, is that the Liouvillean is not unique because it's defined up to constants. And a more fundamental issue is here that due to how this total energy is written, if the Koopman phase vanishes, so does its Hamiltonian functional, which is inconsistent with the prescription rho is equal to psi squared. So, I mean, we are working on addressing these by using non-canonical Hamiltonian structures, but quantum mechanics is canonical, and therefore we would like to restore the canonical structure here. So here's the problem. How do we actually do it? Well, I mean, I don't have time to go into the details here, but a proposal came from Leon van Hove actually in his PhD thesis in 1951. So he was studying how classical mechanics can be looked at from the point of view of unitary representations. And this is really the beginning of pre-quantum theory, which itself is the beginning of geometric quantization, of the geometric quantization program. So there's not going to be any geometric quantization here, but we will use this modification of the KVN Liouvillean, which we called eventually KVH Liouvillean. So what's the important thing here? The important thing is that we are adding the Lagrangian to the Hamiltonian. So in classical mechanics, we are used to stay either on the Hamiltonian side or on the Lagrangian side. Here we carry them both. And of course, as I hinted before, this carries a lot of geometry here. Just want to mention this is a pre-quantum operator and it satisfies a well-defined Lie algebra structure, which will be discussed later on by Francois in his talk. So now let's go back to the Hamiltonian structure and let's perform this replacement here. So from KVN to this modified Hamiltonian. First of all, as Dennis already noticed, H bar no longer cancels. We replace it in the Dirac-Frenkel Lagrangian, and we notice that now the somehow phase space density reads differently. There is the KVN prescription, psi mod squared, plus a divergence of some kind of current, which is written in this way. And when we first noticed it, we got a headache because we had no idea what it meant. But then we realized that this quantity actually does satisfy Liouville equation, the classical Liouville equation. And even though someone will tell me, wait a moment, that's not positive definite, that's fine, at least as long as I'm classical, because positivity is preserved in time from initial conditions by the Liouville equation. And therefore, I decide not to worry too much about this. Now, here's a recap. So we have Koopman on one side and Van Hove on the other side. And the claim is that they actually reproduce the Liouville equation with this expression of the classical density in the box. And now, as already Professor Capral mentioned on Monday, yesterday, it's quite an involved expression. And what I would like to emphasize in this case is that when we integrate these distribution on phase space, the last two terms, of course, they vanish, and we are left with the integral of psi mod squared, so that we are really dealing with square integrable functions here. Now, this is as far as classical mechanics is concerned. Now, let's try to follow George Sudarshan's program and use this modification of the Koopman-von Neumann construction to design a type of hybrid dynamics. And also let's maybe compare these hybrid dynamics to other proposals depending on time. So let's see. So this is how now the quantum classical wave equation is written. So all I have done here, and I want to say very strongly, all I have done here is really changing the classical Hamiltonian with a hybrid Hamiltonian. The way I obtained this hybrid Hamiltonian, as Francois will refer to, and Professor Capral already mentioned yesterday, originally we obtained this Hamiltonian by starting from two classical particles and then quantizing one of them. We would like to see if Dennis' new approach is actually good to derive these type of Hamiltonians also from another way, which is a type of classical limit. Right, so it turns out that these type of equations, I mean, are not new. This is not new. This is not new to us. This was already, this already appeared in Boucher and Trashen's paper from 1988, even though that equation didn't carry the term in parentheses, and it was rejected. It was rejected because of interpretative difficulties. And the authors also claim the absence of a positive conserved energy. Well, in our case, this thing is still a unitary evolution because this hybrid Liouvillean now is again self-adjoint. And so we do have a Dirac-Frenkel Lagrangian. So we have a Dirac-Frenkel Lagrangian for a hybrid theory. And The key thing here is a correspondence
Cesare,
prescription. Sorry.
you'd have 15 minutes.
Oh, 15 minutes. So that's plenty of time. Thank you. Yeah. Correspondence. So we have this correspondence prescription for hybrid observables between, well, what we would normally consider the observable, which is an operator valued function on phase space, into this class of hybrid Liouvillean operators whose algebra will be considered by Francois on a firm mathematical ground in his talk. We can construct, and I will say very clearly, and many of you will be disappointed. This is an unsigned hybrid density operator, and in a sense analogous to what appears in the quantum classical Liouville equation, and it's constructed by well, one way of constructing it is integrating by parts, and the other way is just mimicking what appears in the classical case. Okay, so let's look at what this hybrid operator gives us. So first of all, we look at his equation. We look at its equation, and we do realize it's not closed. So there are the terms up to factors from the quantum classical Liouville equation, but there are also other terms that depend on the quantum classical wave function and its gradients. What happens to the quantum density operator because of integration by parts? We actually realize that the quantum density operator is positive, and therefore, this is an important point that came out briefly yesterday, we do preserve the Heisenberg uncertainty relations in the quantum sector. This is an important point. What happens at the classical level? Well, actually, we are still studying it. So far, we have identified an infinite class of Hamiltonians that preserve positivity of the classical density, but we couldn't get a result in the general case. So I do realize that this may be disappointing to some of you. What happens here? We have no pure states in either classical or quantum sectors. We do have decoherence. Well, we have decoherence in the quantum sector because we lose the pure states, we lose projection states. We also lose delta functions in the classical sector. So let's now look at what happens in a concrete problem. So we wanted to look at the spin-boson problem as suggested by Professor Capral. So first of all, we don't have a code for this equation yet. And so we solved it analytically. We solved it exactly. And the way, we selected the Hamiltonian to solve it exactly. And we selected this type of Hamiltonian here. And we also wanted to look at quadratic coupling, just to think that maybe just thinking that it's more interesting than just linear coupling. So this is how this hybrid wave equation reads in this case. Then there was the problem of designing the initial conditions. So the initial conditions, we wanted to have a Gaussian in the classical sector. And this is how the Gaussian reads in this new weird Koopman-von Neumann Koopman-van Hove context. And then we solved it analytically for an incredibly high coupling constant alpha, 0.95. This is way more than realistic. The important thing about this is that we could reach a class of states that violate uncertainty in the classical sector, okay, by just lowering the temperature lowering the temperature given by the inverse of beta. So what we got here is in a movie, which I hope you can all see. I'm gonna, okay, so this is the movie. So here I have, maybe I should discuss this first. So maybe here in the upper left corner, we have the classical density on phase space. In the lower left corner, we have the coordinates, the configuration density. In the upper right corner, we have the quantum purity, and in the lower left corner, we have right corner, we have the block vector. So yeah. So what happens here is that quantum purity goes down, but then there is a revival of purity after some small oscillations. And this is accompanied by a splitting of the two Gaussians that give the classical density. By the way, in this case, this is the family of infinite family of Hamiltonians that does preserve the positivity. And then we see that actually when the purity goes back to around 1, we can actually, we see again that the classical state has gone back to the usual harmonic oscillator state. And then again, the evolution does its job and takes the purity down again, and so on until the end of this movie. So I will not spend more time talking about this movie because there is not much else to say. So here I want to mention something briefly about, okay, so there are some things we can do, we want to do, but I want to actually discuss an example that was raised by Professor Capral yesterday. So we were looking at the James-Cummings model, and we wanted to compare a class of James-Cummings models with the full quantum evolution. So again, in this case, so the coupling constant is 2 orders of magnitude bigger than those experimentally realized. So in this case, the comparison is with the Pauli equation. And what we obtained is that the decoherence, the lower plot is the decoherence. The decoherence is lower, reaches lower values in the hybrid case. And then the most important effect here is that, well, as Professor Capral was explaining yesterday, there is a sensible difference in the evolution of the block vector, which is actually slowed down quite heavily in the hybrid evolution. Now, maybe this can be, can sound as provoking, but we were wondering if this can be a sign of the Zeno effect. We have no idea. But the other thing I would like to mention is that the oscillator density actually coincides with the Pauli equation and the quantum classical Liouville equation. So okay, so here I will just conclude and I will say thank you.
So do you have any questions? Thanks, Cesare, for the talk. If somebody has a question, you can unmute your microphone and ask. Yeah, we have a few minutes for questions. And
just a small question.
yes, can ask a question.
Professor Bondar. So I was wondering the introduction of the kappa factor and making it go to 0 when you want to see the classical counterpart. Now, in the usual way, when they talk about going from quantum mechanics to classical mechanics, there is a way of taking h cross tends to 0. But you have not done that. You took the kappa factor and kept the h cross as it is. So what motivated you to take the kappa factor and keeping it from 0 to 1 limit? That's it.
Dennis?
Okay, so yeah, sorry, I was just having a problem with unmuting myself. Yeah, so the motivation was actually kind of following a bit Schwinger and earlier work by a Soviet physicist Sokolov, where they explicitly say that, you know, and many other, actually more recently by Bidansky-Birula, emphasizing the fact that actually h bar goes to 0 is actually not a really good limit in Schrödinger equation, and rigorously speaking, and moreover, it appears in kind of in two ways, right? It appears in front of the time evolution h bar, and it appears as the commutator, right? So we wanted to look specifically what happens when you don't touch the time evolution. Sort of, you don't freeze the dynamics by taking this limit, but you actually just take the non-commutativity limit, right? You just make the algebra commutative. And it turns out that, you know, you actually get this, it requires you to build almost the Wigner formulas. You must build Wigner formulas. Again, if you explore this freedom, if you choose this freedom a certain way, right, as I showed. But again, you are not limited. You can choose other way. You can start choosing the freedom in other ways. So in other words, in general, the non-commutativity does not mean the h bar goes to 0, in my opinion.
Okay, thank you.
I also have a question and a remark. Is that okay? Yes? Yes.
Yes, please.
You introduced, Professor Bondi introduced at some point the Bob operators, Bob quantizations. It turns out that these also appear in deformation quantization. Could there be any relationship between your constructions and deformation quantization? That's a question that seems rather natural, having seen what you have done.
So I think it's a very better question to Cesare, but yes, it is actually, it's exactly, in fact, it's what's happening with the hybrids, in the story of the hybrids.
Okay, this is very interesting, actually, yes.
Cesare, do you want to add?
So deformation quantization lies at the heart of Moyal brackets, right?
Yeah, exactly.
So I don't know how this is related to Moyal brackets. I am aware of the connection between the Bob operators and the deformation quantization, but in this context, I would not know how it is related to Moyal.
See, because you see, you pass from, in deformation quantization, you pass from classical mechanics to quantum mechanics by deformation. Well, so
yes.
you perhaps envisage that you deform one part of the Hamiltonian to get the quantum regime and leave the other one unchanged. I don't know, but this is I'm very inspired by your talk.
Yeah, I think that there is a Lie algebra deformation there, which is playing evidently a role, and we don't really know. We didn't really investigate these aspects also because I have to be honest, I don't know much about Lie algebra deformations. So.
Okay.
As you said, Professor Deguson, it's like Bob operators. In fact, this form of the Wigner equation is actually identical to what Bob did up to notation.
Okay.
Yeah, I would like to, Diozi, you can ask your question.
Yep, I have a simple question. These achievements are in the framework of mathematical physics, and the quality of such achievements is independent of the motivations of yourself. But this time I'm interested in your motivations. Do you think somewhere in your mind that there are genuine classical systems, or where hybrid dynamics applies in when those genuine classical systems can become contacted to genuine quantum systems, or on the contrary, you don't believe in the existence of genuine classical systems, but you are interested in good, flexible, effective equations for some fully quantized systems where one subsystem behaves almost classically. So which way did you start from?
So thanks for this question. So I honestly think that all systems are open, right? There's no closed systems, neither quantum nor classical, right? They're open. The open system emerges a kind of limiting case. Sorry, closed system emerges the limiting case, right? So the purely hybrid case is sort of a limiting case of actually both quantum and both quantum system interacting with a larger thermostat. And in fact, historically, right, so with Andre, chair of the session, etc., we published this collaborators. We were very much interested in open dynamics because open dynamics. To model open dynamics, there is still a challenge. Actually, open quantum system dynamics, in particular, as you know, preserving complete positivity is a really difficult task. And in fact, we have actually done this in this work because you can add requirement of complete positivity as sort of here, you can build into the formulas that you want to get your equation motions. So yes, so the answer to the question would be like, we have done a lot of open system dynamics, which I thought would not be a good place to talk about it here with this framework, and that was the original, in a way, motivation for it actually with this work. But yes, I believe that there are perhaps sort of this hybrid. The hybrids I think do exist, and previous talk by Professor Gross, right, clearly shows you that if they don't exist, at least it's good to think that they exist, right? There are very good reasons to think that they exist. And of course, like your work and other people here on the gravity, right? We have no evidence yet that the gravity is quantum. I mean, we may not even get that right. And this is like another thing that I was interested in entropic gravity from this perspective. Thank you for this question. I hope I answered it.
I have a question, if I could.
Yes.
I'm curious about looking at observables, say that depend on the Bath variables. So you mentioned that only a portion of the density matrix appears for subsystem variables. But if you consider Bath variables, then you have to consider the full expression for the density. Now, one thing that I find interesting, and it'd be, I think, interesting to work out, is that if you consider, say, a subsystem observable, then you can compute it along the lines you mentioned. But for instance, that's a particular choice of representation. And if you instead, say, go to an adiabatic representation, then just by a unitary transformation now, the corresponding variables depend upon the Bath coordinates as well. So all of a sudden, a much more complex structure arises. And so I'm wondering if you thought about that.
Shall I answer or
yeah.
Okay.
Yeah.
So I mean, I have a tentative answer. Well, I don't. Okay, let me say one thing. So we did think of using different bases to express these Liouvillean operators. And actually, a convenient basis was already provided long ago by Mauro in Italy, in which he moved away from the QP basis to go into the Q lambda P basis, where lambda P is the operator that Dennis introduced. And he showed that actually the structure of the Liouvillean is much is simpler in a way in that case. Now you are mentioning a different kind of basis because you are thinking of the basis that is used in the Born-Huang context. This is something that I quickly looked at, but I didn't find anything interesting, to be honest. However, you also mentioned while you were talking the possibility of having wave functions parametrized by some coordinates. And on that, I will tell you that we are actually working. I personally am working a lot on applying the exact factorization that Professor Gross introduced in the earlier talk. And I am finding a lot of interesting things. including finite dimensional closures, and also I think for this type of systems, it's even possible to remove the ambiguity or in the sign of the classical distribution. But this is ongoing work, which at the moment is looking very promising.
Okay, so let's just see one last question from Mustafa. You can ask your question, and then you should move on to Professor Elsa's talk.
Hello, can you hear me?
Yeah.
Hi.
Okay, thank you for the talk. That was really nice. I have a question about the introduction of these lambda variables that are a conjugate to x and p. So we have the x and lambda x, p and lambda p. Is that correct?
Yeah, that's right.
Yeah. So in what sense is p the momentum if it's not canonically conjugate to x?
It's a classical physics, right? In classical physics, there's no conjugation, canonical conjugation between position and momentum, right? So they commute, they have to commute, but that's at least that's what I, myself, like Schwinger, I should not speak on behalf of Schwinger, but Bielski, Berula, Solovyov, this would be quantum case. That would be classical community. Why you need the lambdas? Because if you don't have them, and if you apply this technique, you will get a contradictory conclusion that there is no dynamics. Like you reach in fact, you reach a contradiction. Like you reach a contradiction, there is no L that can describe this evolution. You must introduce them. And that's another nice feature about ODM is that if you put two inputs that are incompatible, you can use this to build the no-go theorems. We actually, in fact, showed some no-go theorems that some things are not possible.
Right.
And it can also suggest you how to fix this. In this case, it suggests you what to fix. You need to introduce these additional variables to break this no-go.
Okay, I just want to, I'm trying to build a picture of these kind of dynamics. So you propose, or I mean, Koopman-van Hove or whatever, would propose that we have quantum conjugates, x and lambda x, like a commutator, non-vanishing commutator between x and lambda x. So it acts as if it's a momentum in the sense that it does not commute with x, but we have the classical x and p. So x and p would satisfy the Poisson relation, but x and lambda would satisfy the quantum or the commutative relation. Is that correct?
That's
so
right,
we have some kind of a lambda is like the quantum momentum conjugate to this classical thing. Is that correct, or what?
It's correct, and in fact, it's exactly why commutator here takes the role of the Poisson bracket. It's literally constructed so that there is equality between exact equality between commutator of the Poisson bracket in this language.
Okay, thank you.
Or rather, I should say, commutator is a representation of the Poisson bracket.